So in this part of the chapter, you're going to learn more about chemical bonding and how atoms bond together in order to form molecules. So how exactly do atoms bond together in order to form molecules or compounds? How do chemical bonds form, and how do we know that they are stable? Well, in order to answer these questions, we use what they call bonding theories. Okay, and if you remember, a theory is basically an explanation that of a specific observation that's been supported scientifically. Okay, supported by scientific data or scientific evidence. So bonding theories are basically models that predict how atoms bond to form molecules or compounds. They can explain the stability and reactivity of molecules, and they can be used to predict the shapes of molecules. So this third one here, shapes of molecules, that's very, very important because all your cells in your body interact with each other via recognition. Okay, so if they recognize a specific shape, then they'll be able to identify whether that cell is defective or not. Cells interact with foreign matter, right? Foreign antigens. And so if they think that an antigen is harmful to your body, then they will send specific signals to the rest of the body and basically recruit the specific cells to combat those antigens. And of course, there are many different models and theories out there to explain a specific phenomenon, some of which can explain certain observations a lot better and more accurately than others. And the simplest model that you're going to learn today is the Lewis model. And this is also known as the Lewis theory. And what it is basically it uses Lewis dot symbols. And so in this model, Lewis structures, also known as the Lewis electron dot structures, are drawn to illustrate molecules, and the valence electrons are represented by dots. So it's sort of a more advanced Lewis dot symbol, because the Lewis dot symbol is specifically for a given element. So you learned that in the previous lecture. But now you have a bunch of elements that are bonded together, forming a chemical bond. And so now you have a structure. And they call this the Lewis dot structure. And it can be used to predict whether a set of atoms will form a stable molecule and what it would look like. In the first part of this chapter, you learned that atoms form molecules or compounds via chemical bonds. And there are three different types of chemical bonds. There's ionic bond, covalent bond, and metallic bond. Metallic bond, we're not going to cover this in great detail, but you should know that there are three different types of chemical bonds. The first type here is ionic bond, and this is the bond between metals and nonmetals in which electrons are transferred. So metals tend to lose electrons, and then the nonmetals tend to gain electrons. And so the electrons that are lost from the metals are gained by the nonmetals, and hence you have a cation and an anion, a positive charge and a negative charge, ions that are interacting together via ionic bonding. Covalent bond, on the other hand, is a bond between nonmetals only. And in this type of bonding, the electrons are shared by the elements or by the atoms. And so it's completely different from ionic bonding because the electrons are being shared instead of being transferred. In metallic bonding, the bond is only between the metal atoms. Okay, and so the electrons are delocalized throughout the entire metal structure. So in ionic compounds, right, like sodium chloride, basically salts, you have magnesium fluoride, aluminum oxide. In ionic compounds, they utilize ionic bonding, okay, because you have a cation and anions interacting via ionic bond. In covalent bonding, you have molecular compounds or molecules that are sharing electrons, valence electrons. So, for example, hydrogen gas has the chemical formula H2, and so you have a pair of electrons that are being shared by the two hydrogen atoms, and these electrons are shared equally by the two atoms. Now, in hydrogen fluoride or hydrofluoric acid, the electrons, the valence electrons, are not are shared unequally by the two atoms. And then finally, in metallic bonding, you have just pure metals, basically. So you have sodium metal, silver, gold metal, and so on and so forth. And the electrons are, or the atoms, the metal atoms are basically submerged in a pool of electrons. In the beginning of this chapter, you learned about Lewis symbols. And Lewis symbols basically contain the symbol of the element, and that element is surrounded by dots. And the dots are represented by the valence electrons, these valence electrons. And so, for example, sodium has a symbol Na, and then it has one single dot because it only contains one valence electron. And then you have calcium, and calcium has a symbol Ca, and it's a group 2 element, and so it would have 2 dots. Boron would have 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, neon 8. So you should be completely familiar with Lewis dot symbols because Lewis bonding theory utilizes Lewis symbols. And here's another recap from the first part of the chapter, that atoms with 8 valence electrons are considered stable because they have full S&P sublevels. In other words, they are isoelectronic with the noble gases. And another way to put this is that they follow, or they satisfy, the octet rule, the rule of 8 valence electrons. And of course, there are some exceptions, and we'll talk about that in more detail here. So all the noble gases are considered unreactive. They're very stable. They are the most stable elements in the periodic table. And the reason why is because they have a full octet. They have 8 valence electrons, except for helium. And helium doesn't have a full octet. In fact, it only has 2 electrons. So 2 valence electrons. Helium, the first noble gas, is just as stable as the rest of the noble gases, even with only 2 valence electrons. So it doesn't have an octet, but it has a duet, as they call them, right? 2 valence electrons in its outermost shell. And so when you imagine a helium atom using Bohr's model of the atom, the first orbit, or the first energy level, contains the maximum number of electrons. Right, so it has 2 electrons. So that means that the first energy level is already completely filled. And because it's completely filled, it's considered stable and unreactive. And you also learned that group 1A elements, the alkali metals, are very reactive metals. And the reason why is because they contain a single valence electron. And a lot of alkali metals tend to lose a single electron in order to become isoelectronic with a noble gas. And so they want to get rid of that single valence electron that they have in order to stabilize themselves by forming an ion, cations. So chemical reactions happen because you have elements that are unstable. And elements that are unstable will form bonds with other unstable elements in order to achieve stability. And when we say stability, that means isoelectronic with a noble gas. So when they form a bond, those 2 elements that used to be unstable now become stable. And when these elements form a bond, they either share or transfer electrons to get the full octet. So in other words, these elements now become isoelectronic with the noble gas. And chemical bonds form via 2 ways, as you learned earlier, via ionic or covalent. right? And so ionic is the transfer of electrons from a metal to a non-metal, and then the covalent is by sharing electrons, whether it's by equal sharing or unequal sharing. In both cases, the atoms involved in bonding will obtain a complete octet or a stable electron configuration. So it becomes, again, isoelectronic with a noble gas. This is known as the octet rule, rule of 8 electrons. So now let's compare ionic bonding from covalent bonding. So in ionic bonding, you have the transfer of electrons, whereas in covalent bonding, you have the sharing of electrons. So how are electrons being transferred from a metal to a non-metal via ionic bonding? So let's take a look here. So for example, you have potassium ion, a cation and an anion, potassium and chloride ions, forming an ionic compound, potassium chloride. Right? So the metal contains one valence electron. And so this valence electron coming from a metal, potassium metal, will be lost, will be donated to the non-metal, which is the chlorine atom here. So this chlorine atom contains seven valence electrons because it's in group 7. And so in order to have a full octet or 8 valence electrons, it needs another electron. And that electron can be obtained from a metal. It could be a group 1 metal, could be a group 2 metal, or group 3. It doesn't matter. As long as it is a metal that can donate an electron. So when it donates an electron, that potassium gains a positive charge. And so that chlorine, once it receives that electron, it gains a negative charge. So now you have a positive negative interaction here, an electrostatic interaction. And that's basically what ionic bonding is. It's electrostatic interaction between a cation and an anion. And in that process, you have this potassium ion becoming isoelectronic with argon. So potassium has 19 electrons, right? And then it donates one of its electrons, the valence electron. Now it becomes 18, right? Now it contains 18 electrons. Argon also has 18 electrons. And so because they have the same number of electrons, they are isoelectronic. And chlorine, on the other hand, gains an electron. And so it originally had 17 electrons. It gained one additional, so now it has 18 electrons total. So it's isoelectronic with argon as well. And we can look at it in terms of electronic configuration. We can write the electronic configuration for a potassium atom. So again, potassium has a total of 19 electrons. And so that would be 1s2, 2s2, 2p6, all the way to 4s1. So when you add up all the superscripts or the exponents here in purple, that should add up to 19 electrons. And then this potassium atom will lose one electron. And that would be coming from the 4s sublevel. So we will lose this electron here. And now you have this electron configuration for a cation, for the potassium ion. So it's 4s0. That tells you that that 4s is now empty. And you can see that this electron configuration of a potassium ion is the same as the electron configuration of the argon noble gas. And we can do the same thing for chlorine, right? So chlorine has 17 electrons. So this is the electronic configuration for chlorine. You can see that the S and P sublevels are not completely filled. It only has a total of 7 electrons. And so by gaining one electron, it becomes isoelectronic with a noble gas, again, argon. Now, covalent bonding is the complete opposite of ionic bonding. So here you're sharing electrons instead of transferring electron. So the electrons are being shared by the elements involved in that chemical bonding. And so Lewis dot structures can be used to show how atoms are bonded together using Lewis symbols. So we can look at a diatomic molecule for simplicity involving only two elements. So that's what diatomic means. You have two atoms or two elements. So let's say we want to draw the structure for a fluorine gas. And the chemical formula for fluorine gas is F2, right? So you have two fluorines. So the first step here is to basically to draw the Lewis symbol for each atom. Okay, so you draw the Lewis symbol for one fluorine and then another for the second fluorine. And then we're going to incorporate or apply the octet rule, meaning how are the electrons being shared in order for both elements to have a total of 8 valence electrons. How do they satisfy the octet rule? So here's the Lewis symbol for the first atom of fluorine, and then the Lewis symbol for the second atom of fluorine. So you can see that each fluorine atom lacks one single electron. And so how can they form a bond and satisfy the octet rule? So each fluorine then will share its single electron here that's unpaired, right? All the rest of the electrons here are paired. And so they can form a bond by sharing the electrons. So now you can see that each fluorine atom has a total of 8 valence electrons. So you can count them. For this fluorine, you have 2, 4, 6, 8 electrons. For this fluorine, the same thing, 2, 4, 6, 8 electrons. So both fluorine atoms now have a complete octet, and so they satisfy the octet rule. This pair of electrons here that are being shared by both atoms are known as, or is known as, a single bond. Okay, so we'll take a look at that right here. So we have this pair of bonding electrons, and we call this a bonding pair. So any bonding electrons are known as bonding pair of electrons. And this is basically what a single bond is. And the electrons that are not involved in bonding are known as non-bonding electrons, aka lone pair of electrons. And this bonding pair of electron is usually represented by a line, a single line. And so a single line is known as a single bond. So you always want to remember that a single bond contains one pair of bonding electrons. So that's basically the structure, the Lewis structure for a fluorine gas or fluorine diatomic molecule. Now, what would the Lewis structure for oxygen gas look like? So we can do the same thing here. We can follow the same steps as we did for fluorine gas. So step 1 is you draw the Lewis symbol for each atom. And then the second step is to apply the octet rule. So for the single oxygen atom on the left, we have the Lewis dot symbol. And then for the second atom, we also have the Lewis dot symbol here. So you can analyze the two atoms, and you can see that they only contain 6 electrons. And so they each lack 2 electrons to satisfy the octet rule. And so what they can do here is to share a total of 4 electrons, right? And so these 2 electrons right here will be shared with this oxygen. And the same way, these 2 electrons from the second oxygen will be shared with the first oxygen. So in other words, they can basically share a total of 4 electrons. And whenever you're counting the total number of electrons for each atom, you can see that this oxygen right here has a total of 2, 4, 6, 8 electrons. Same thing for the first oxygen, 2, 4, 6, and 8 electrons. And again, one pair of electrons is represented by one bond. Now you have a total of 4 electrons here. So that would be represented by 2 lines. And this pair of lines right here is known as a double bond. Okay, so a double bond contains 2 pairs of bonding electrons. Now let's look at another diatomic molecule here. This is nitrogen gas with the chemical formula N2. How do we draw the Lewis dot structure for nitrogen gas? Well, again, we will follow the same steps here. The first step is to draw the Lewis dot symbol for each atom that's involved. And then we'll apply octet rule. So here's nitrogen. So you have the Lewis dot symbol for the first nitrogen here and the second nitrogen here at the bottom. And you can see that each nitrogen has a total of 5 valence electrons. And it has to have a total of 8 in order to follow the octet rule. And so it lacks 3 electrons in total. Each nitrogen lacks 3. And so these 3 electrons here will be shared with this second nitrogen. And these 3 electrons from the second nitrogen will be shared with the first. Alright, so basically they're forming 3 bonds. Okay, so you have 3 lines. And so you have a total of 6 electrons that are being shared equally by the 2 atoms. And you can simplify this Lewis dot symbol structure using lines. All right, so this indicates that you have 3 bonding pairs and a total of 2 lone pairs. So these 3 bonding pairs are also known as a triple bond. What about hydrogen? Hydrogen is actually a special case. So we can draw the Lewis dot structure for, let's say, a hydrogen gas. And a hydrogen gas has the chemical formula H2. So it has 2 atoms of hydrogen. Hydrogen doesn't have to follow the octet rule, meaning it doesn't have to have a full octet. It doesn't have to have 8 valence electrons. And but as long as it becomes isoelectronic with a noble gas, then it's considered stable. And so hydrogen gas, H2, becomes isoelectronic with helium. And helium contains 2 electrons. And so for hydrogen gas, H2 here, we can follow the same step, the same 2 steps. You draw the Lewis dot symbol for each atom. So here they are. We have the Lewis dot symbols for a hydrogen, and then both electrons are being shared by both atoms of hydrogen, and they form a single bond, a single line. And this, again, as I mentioned earlier, this is considered stable because they are isoelectronic with the noble gas helium. Here's one example of a compound containing more than 2 elements. So here we have ammonia with the chemical formula NH3, and you can see that ammonia has nitrogen as its central atom, and the nitrogen is bonded with a total of 3 hydrogens. So with ammonia, this is a compound that's colorless and it's in gas form. It has a really pungent smell. It's considered caustic and hazardous, and this is usually used as fertilizer and cleaning agent. If you're in a organic chemistry lab, you use ammonia as a solvent. And so, what type of compound is ammonia? So on the test, I may ask you what type of compound is shown here. Right? I'll give you an image or a chemical formula, and then you have to figure out what kind of compound it is. There are only 2 types of compounds that we looked at. There's ionic compound versus molecular compound. And so you would base it off of the elemental composition. So you have all nonmetals here, right? So if you have all nonmetals, then it must be a covalent compound or a molecular compound. What would be the type of chemical bonding utilized here? Well, because we have a covalent compound or a molecular compound, it has to utilize covalent bonding. How many number of shared electrons? Okay, so this is a pair of bonding electrons. Here's another pair. So a total of 2, 4, 6 shared electrons. Okay, or 3 pairs of bonding electrons. Number of unshared electrons. So this is 1 pair right here. So you have a total of 2 unshared electrons. And last one, does the nitrogen have a complete octet? Does it? Well, we can count. So this is nitrogen right here. 2, 4, 6, 8. So yes, it has a complete octet. So here's another compound called sodium azide, and it has the chemical formula NaN3. Shown here is the chemical structure, or the Lewis dot structure, of sodium azide. So there's sodium here and then a bunch of nitrogens that are bonded together. Sodium azide is colorless and known to be toxic and poisonous. They are used in airbags, and so airbags is basically a chemical reaction that produces a huge amount of nitrogen gas. And sodium azide is also used in organic and inorganic synthesis. So what type of compound is sodium azide? Well, you have to analyze this compound. You see that you have a metal here, and clearly it's an ion, and the azide ion right here with negative and positive charges. So this compound is an ionic type of compound. What about type of chemical bond? So because you have positive and negative charges, it utilizes ionic bonding. But then when you look at the anion here, this anion part utilizes covalent bonding because you have a bunch of nonmetals that are chemically stuck together. So it uses covalent bonding, both covalent bonding and ionic bonding. What's the number of shared electrons in azide? Okay, number of shared electrons in the azide ion. So this is the azide ion right here. So we have 2, 4, 6, 8 shared electrons. Number of unshared non-bonding electrons in azide. Okay, so we have 2, 4, 6, 8 non-bonding electrons. And finally, does the nitrogen have a complete octet? Each nitrogen. So let's look at each nitrogen here. This nitrogen is essentially the same as this nitrogen right here. You have 2, 4, 6, 8, 2, 4, 6, 8. And then this nitrogen in the middle also has 8 valence electrons. 2, 4, 6, 8. So yes, they all follow the octet rule.